A few weeks ago, I released a video on Lambda Snapstart for .NET just after Snapstart came out, and let's just say things maybe didn't go quite as well as might have been expected. As we start to run this query more, you can see that the cold start numbers are still pretty high. The P50 cold start here is about a second. Now, you might think that is not quite as impressive as you might think. Frankly, you might look at that and think that's basically just the same as not using it. I give a direct comparison from that Snapstart enabled function to the exact same function deployed without Snapstart. So here it is. Here is the .NET 8 ASP.NET Minimal API deployed to Lambda just using latest, no Snapstart, the exact same configuration, apart from Snapstart has been turned off. And the numbers actually in this case are better. You are better off not using Snapstart in this scenario because when there is a cold start, there are both less cold starts and the maximum cold start is about 1.9 seconds. You'll remember from the Snapstart enabled video, the maximum cold start was over 2 seconds. Given that Snapstart is a really cool announcement, but when it came to hosting a bigger ASP.NET application inside Lambda, it didn't really have the performance impact that I thought it would. In fact, as you just saw, sometimes it even made things a little bit slower. Not what you want from a service that claims to boost performance for .NET on Lambda. But here's the thing, I don't actually think Snapstart should be considered as a performance feature. Interesting, right? But if you were building a brand new .NET application to run on AWS Lambda, you would probably use native AOT. Well, because if you're building something brand new from the ground up, you can work with the constraints that native AOT puts upon you. Where I actually think Snapstart is better placed as a modernization feature. It gives you the potential to take an existing ASP.NET application and run that on Lambda, which is why that last video was kind of disappointing because, well, it didn't really make all that much difference. However, kudos to AWS, particularly to David Palman for setting up a conversation with AWS and PJ Pittle, one of the engineers on the .NET team, to actually go and do the work, because I spent about an hour on the phone with the folks at AWS, and this is what came off the back of it. What we actually realized was that when you're running ASP.NET on Lambda, although you have the ability to run code before a snapshot is taken and run code after a snapshot is restored, and one of the benefits of doing that is to be able to warm up, to pre-JIT the hot paths in your application. But if you're running ASP.NET on Lambda, there was no way to actually warm up ASP.NET itself. You couldn't pre-JIT some of the hot routes on your API because there was no way to call ASP.NET from inside your startup class. That's all changed now. One of the things added in the last week is this ability to define AWS Lambda before snapshot requests. You can pass in as many of these as you want, and whatever HTTP request message you define in this method, they're going to be sent through the ASP.NET middleware pipeline, through your application code, back out the other end, and it's going to do that as part of the snapshotting process. What that means is that you can pre-JIT a whole bunch of hot routes on your actual application paths. This means that any runtime optimizations, things like tier compilation and all that other good stuff is going to have happened before the snapshot is taken. That means that snapshotted image of your ASP.NET application, as soon as an actual request comes in, it's all hot, it's all warm, it's all ready to go and handle that as fast as physically possible. So what does that actually mean for performance? So what I've deployed into my AWS account are 3 different Lambda functions, all using the exact same underlying application code. This is a monolithic application of the plant-based pizza. You can find this on GitHub. There's a link in the description below. It's a pretty standard .NET application. It's a modular monolith, if you will, and it uses Postgres as the underlying database provider. I've used Postgres to try and kind of replicate a more traditional .NET application where you've got ASP.NET and you've got some kind of relational database. In this case, I'm using Neon. If you're not familiar with Neon, they've just been purchased by Databricks. They're an incredibly powerful Postgres database provider, fully serverless Postgres, scales up, scales down. You can branch your database, all sorts of good stuff. I'm going to do another video on that in the future. So I've got these 3 Lambda functions, 3 different deployments of the exact same ASP.NET application. And there's differences here. The first one is just a base .NET application. This is just a standard Lambda function. Lambda function URLs to handle the API requests. This is just ASP.NET running on Lambda. Nothing fancy here. I've then got a version of the function with Snapstart enabled. This is with Snapstart enabled, but without some of them optimizations that I've just shown in that blog post, where I can send requests through the middleware pipeline as the snapshot is taken. And then I've got a third Lambda function, which is pre-warmed. This is where I am sending through that set of requests as part of the snapshot process to to pre-warm all of the hot paths in the application code. So what difference does this actually make? Well, let's start out with the actual base Lambda function. And to do this, I've hit this API endpoint with 100 requests a second for a minute. And then I'm running a CloudWatch query here to filter this down to only show me the inits. So you can see with this Lambda function, this is just ASP.NET running on Lambda, connecting to a Postgres database. You've got about a 4-second duration, between 3 and 4 second duration. That's made up of about a 3.5 second initialization. You can see that in the init column there, and then a sub-second invoke duration. And there's a little bit of variability in here as this endpoint gets hit more and more. One of the other really interesting things is that there were actually 279 cold starts. Now, that's 279. If I just remove that query there, that's 279 cold starts out of a total of 6,000 invokes. So now, 4 seconds isn't ideal if you're a front end calling this application waiting for a response, which is why SnapStart exists, right? So let's go and have a look at this with SnapStart now. And let's first have a look at the function with SnapStart. This is without the pre-warming. So I'm going to run that same query, and I've sorted this by total duration. And you'll immediately notice there's less than half of the cold starts. Now, this is simply because if an API can handle requests faster, that means the execution environments are returned to be available waiting for a request faster, which means you've got less total cold starts. So you're already seeing less than half of the cold starts. 122 cold starts out of, let's just update this query again, out of, I would guess, a similar number. Yeah, 6,000 invokes, 100 requests a second for a minute. Kind of should have done that maths myself, shouldn't I? And immediately, you'll see these numbers are much better. We've got a total duration now of 1.6 seconds. So SnapStart there has made about 50% difference to the performance. As we scroll through these numbers, you'll see it's pretty consistently through all the invokes over a second. 1.2, 1.3, up to 1.5, 1.6 seconds. There are these small number of invokes down at the bottom here that take about 900 milliseconds. Now, there's a bit of variability here because of the way SnapStart works. If you can think of the internals of SnapStart a little bit like a cache, when you first take a snapshot of a function, it takes a little while for that snapshot to be hydrated around the internal Lambda cache, if you will. So what you will typically see if you're using SnapStart is over time, this restore duration will get lower and lower and lower. So looking at these numbers in a little bit more detail now, we've got a restore duration of about 300 to 400 milliseconds, maybe up to 500 milliseconds near the top. The restore duration is pretty consistent here. And then the actual duration of the invoke, remember, this is the first invoke that's hitting a restored snapshot, is about 800 milliseconds, 700 milliseconds, 900 milliseconds. It's nearly a second for the actual invoke to happen. So that's just with SnapStart. Let's change this one more time now and look at the pre-warmed functions. And you'll see that there are a similar number of cold starts. We can have a look at what that is maybe in the future. And now looking at these durations here, now you might initially think, that's slower than without the pre-warming, which is interesting, right? But as we look through these numbers, you'll see a bigger proportion of the requests are being handled in less than a second. Looking at these numbers here, the vast majority of the requests, actually, I'd say over half of these requests are sub-second response time. Now, sub-second response time is typically about the tipping point for a front end to be acceptable. That's what at least we found when I used to work at AWS. Sub-second was acceptable for the vast majority of workloads. So you've got over half the requests here being handled sub-second now. And the biggest difference you'll see is actually in this duration column. You'll see that the restore duration is pretty comparable to when this was not being pre-warmed. 500, 600, 700 milliseconds just to restore the snapshot. Where the difference is happening is in this duration column. This is because these endpoints have been pre-warmed as part of that snapshotting process. That means they're fully jitted, all the optimizations have been happened, everything is ready to handle these requests as fast as possible, which is why we get 200 milliseconds, 100 milliseconds, the kind of performance you will probably come to expect from a .NET application. Now, of course, some of these numbers up at the top here do get a little bit longer. A second here, this could be something at the database angle. I'd need to add some observability to these functions. Maybe we should observe exactly what's happening here to work out exactly what is causing these durations to be longer than these ones that are considerably quicker down at the bottom. So, pre-jitting, how do you actually go about doing this? So let's have a look at my actual application code now. So I've got pretty standard ASP.NET application. We've got a program.cs file that adds various things, logging, it adds all the various different modules, it adds a whole bunch of other stuff. I've got in my actual startup, I've got this add Lambda extension method. This is just centralizing all of this configuration to set up if this application is running on Lambda. The first thing we're going to check is if the environment variable Lambda task root exists. All this means is that this exact same application can run on ASP.NET, on a container, or on Lambda. If that environment variable exists, that means that the application is running inside the context of Lambda. We're then going to add the AWS Lambda hosting. This is a method that comes from the Amazon Lambda ASP.NET Core Server NuGet package. This is what allows you to just run ASP.NET inside Lambda. And then I've got this pre-warming code here. Notice I've got this environment variable set pre-warm equals yes. That's so I could separate between the version with pre-warming and not with pre-warming. And then all I'm doing is adding these AWS Lambda before snapshot requests. And you'll notice I'm iterating 15 times here. That means that when this application is snapshotted, the /recipes endpoint and the /health endpoint are going to be hit 15 times each. The optimizations that .NET Runtime applies will get applied as the same code paths get hit more and more and more, because the runtime can treat them as a hot path in your application. So hitting these 15 times, 20 times, 30 times, remember, this is happening as part of the snapshotting process. All you've got to worry about is a 10-second max execution time. If your snapshot takes longer than 10 seconds to be taken, then you're going to have some issues. So as long as all of this stuff you're doing as part of your snapshot happens inside 15 seconds, everything will be okay. So we're running 15 iterations and we're setting 15 calls to the /recipes endpoint, 15 calls to the /health endpoint. Now, one final thing to be aware of, something that I've noticed as I've been working with this, is that intermittently the first invoke after a snapshot is restored can sometimes have issues. Now, like I said before, I'm working with Neon as a Postgres database provider here, and Neon supports connection pooling, so all the pooling happens Neon side. If I use Neon with pooling enabled, I seem to pretty consistently get some kind of exception on the first invoke. I can only assume is that the snapshot is taken with a connection to one database inside the pool. Between the snapshot being taken and the invoke actually happening, that underlying database is changing somehow, which means that connection is no longer valid, which means the first invoke fails and then retries. And if you're not familiar, Entity Framework supports this idea of enable retry on failure. So what this is going to do is going to retry up to 2 times for this specific DB context. So that means that if there is some kind of transient error with the underlying database connection, it's going to retry, hopefully make that connection, and then invoke. That is probably what is causing these slightly slower durations. There's probably another test to run at some point with pooling disabled on the Neon side, just to see exactly what happens. Now, for me, this starts to make running ASP.NET on Lambda a much more convincing option for your existing applications. When you think about the simplicity of just being able to take your ASP.NET application, push it up to Lambda, add a function URL, and there you are. You've got a highly scalable web application running in a way with next to no operational overhead. And with the snap start functionality, plus this ability to pre-warm specific endpoints on your API, this does make running bigger applications inside Lambda a much more convincing option. Now, of course, if you're building net new workloads, you're starting a brand new project, working with .NET, working with Lambda, look at native AOT. You're going to get better performance with native AOT than you will with snapshotting a function. And because you're building from the ground up, you can pick and choose the libraries you want to use that are AOT compatible. But if you've got these bigger existing applications, you just want to run them and you don't want to think about infrastructure. The other interesting thing with the cold starts is that you're actually likely to see less cold starts with a bigger application running on Lambda. If you've got multiple routes on your API all being handled by the same Lambda function, you're likely going to see less cold starts than having all of them API endpoints on a range of separate Lambda functions. So that's just something else to keep in mind, the pattern of the Lambda lith as it is commonly known. The final thing I will say on all of this is if you are looking at running anything on Lambda, whether it's a .NET application, whether it's a Python application, a Node application, when you deploy it, always run some real world load through your function to understand if it actually impacts or not. take this application that we've been looking at today. If I was to look at just the cold starts for this pre-warmed Lambda function, I can see that there's been 154 cold starts. The time that the total response time of this Lambda function ranges from 1.7 seconds right through to 300 milliseconds. I mean, 300 milliseconds on a cold start with .NET ASP.NET is terrifyingly good. But when you consider that in the wider context of 154 cold starts, 50% of them are sub-second, they'll be fine, 50% aren't. When you consider that alongside the fact that there were 6,000 total invokes of this Lambda function. I'm not doing the maths on the top of my head because I'll get it terribly wrong, but that's a very, very small portion of the total requests are actually cold starts. So however you're running your application on Lambda, run some real load through it to see if it's actually going to have an impact. As you're developing Lambda functions, you're likely to see a lot of cold starts. But actually, when you look at it across a more macro view, across a whole range of invokes, across an actual profile of load that your application receives, you probably find it's less impactful than you might think. As I scroll down through some of these lower requests, you'll notice that the duration on some of these requests are 9 milliseconds, 16 milliseconds, 14 milliseconds. Incredible performance, which we all know .NET has. Considering we've got Postgres under the hood as well, these are terrifyingly good numbers. So that's SnapStart for Lambda. Kudos to the team at AWS for taking the feedback on board and adding this new functionality to be able to actually pre-warm these endpoints before you deploy them to Lambda. And genuinely, it's making quite the impact on performance. I'll see you all in the next video.